Hello and welcome to our BayesiaLab webinar today. Thank you so much for joining me. My name is Stefan Conradi and I'm the managing partner of Bayesian USA. I will be your webinar host today. Here's today's agenda. We'll start off by talking about our motivation and challenge, which is that simulations are fast, yet they can be very slow. You'll soon understand what I mean with that. Our objective is to overcome this challenge by simulating the simulation. I know this sounds funny, but at the end of this webinar, you'll hopefully agree with me that this can be a rather clever approach. I'll explain the proposed methodology with a case study that deals with vehicle suspensions. That is tires, springs, shock absorbers, etc. While this is obviously an automotive topic, which car guys like myself will definitely enjoy, I promise that this is actually a very generic type of problem that applies to many fields of study. So here's our actual workflow. I will tell you about the principal technical simulation, which I've prepared offline because it takes a while to perform. And this is the simulation that we will then approximate with a Bayesian network model. I will show you how we can machine learn such a Bayesian network model with BayesiaLab. Then we can experiment with that new Bayesian network model and optimize the parameters, in our case, the suspension parameters. Finally, we publish the new Bayesian network simulator with the BayesiaLab web simulator. Let me perhaps now put that into context. Many of you will have seen this particular diagram before. And I'll show you how our workflow belongs in here. First, we perform knowledge discovery from data to build a Bayesian network. That is very common, and you have probably seen that before on many occasions. Then we use that network to simulate and optimize. The difference today is that we will machine learn from machine-generated data, meaning from the output of another simulation. Additionally, towards the end, we will also introduce expert knowledge, which will be quite an interesting twist. So we will add domain knowledge in addition to the machine-learned knowledge. And of course, we will be using BayesiaLab, our software, BayesiaLab 8, more specifically, to learn, to edit, to analyze, simulate, and finally optimize with our Bayesian network. Let's talk about our motivation. In engineering applications, we generally deal with systems that handle inputs and produce outputs. And the way inputs get transformed into outputs depends on parameters. In a very simple application, parameters can perhaps be optimized analytically. For instance, when you design a filter for an audio signal or something like that. In more complex domains, analytical solutions are no longer feasible. So it means we need to experiment to try out what works best. Needless to say, experiments can be slow to conduct and typically very expensive because it involves creating hardware, setting up test rigs, and so on. Now, with advancing computing power, however, such systems can now be simulated. Still, given the number of possible parameters and different parameter values, this can still be quite a slow process. It can be very time-consuming, requiring a lot of computing resources. So what we're trying to do today is simulate the simulation. Basically take the very, very detailed simulation model, a mathematical simulation model, and machine learn from it to create a meta model that approximates the original simulation model. So that's what we're trying to do today. So this new meta model approximates the behavior of the original model. Often in other contexts, this is also known as response surface modeling. And you can use many techniques for that. We're going to use Bayesian network. So we'll have a Bayesian network meta model. Now, before we can actually start building our meta model, we need to build the proper model first. Here, basically creating the source material for our subsequent learning. So we'll need to take a step back and talk a little bit about our problem domain. So as you already know, our case study topic deals with vehicle suspensions. Now, as a caveat, I need to add we will be looking at a highly simplified example. And so I will omit many engineering terminology conventions. I'll simplify notation, scaling, etc. So we don't have too many distractions. After all, this is not about optimizing a vehicle suspension, but rather this is about introducing the Bayesian network methodology. So in the spirit of simplifying, we will not be looking at the suspension of an entire vehicle. Rather, we will just be looking at the suspension of a quarter, 1/4 of a vehicle, meaning one wheel tire combination plus the corresponding suspension parts and body components. Also, we will only consider the body and the mass of the body concentrated into a single point. So this is obviously very, very simplified compared to reality. But let me illustrate this a little bit now. Here we have a visualization of the simulation model. And we can see all the components here. First, we have a linear spring, shown here as a blue coil spring. Secondly, we have a damper, more commonly known as a shock absorber, here shown in yellow. And then furthermore, at the bottom, we have the vertical road displacement that provides the road input, the road irregularity. And then finally, at the top of this assembly, we have where the vehicle body is mounted. And as I said earlier, all the vehicle's mass, or the mass of the quarter vehicle, is concentrated in a single point. So that's our main suspension setup. But there is more to it, because we have a wheel tire assembly. And that means the tire itself has some certain dynamic properties as well that we must consider. And that is the tire acts as a spring, and also it has some damping properties. So we will need to include that in our model. As for the mass of the wheel tire combination, here we're also assuming a point mass. So consider that all the mass of the wheel tire combination is concentrated at the wheel hub. So now let's translate that into a mathematical model, and that is basically assembling a whole bunch of differential equations. Now I've implemented this model using the Wolfram System Modeler, and that offers a very convenient interface to build and simulate this kind of model. But there are others. There's Simulink. And all this is based, most of these modeling tools are based on the Modelica modeling language. So this is really independent of any particular vendor. Anyway, here you see how each individual component of the previous illustration is now reflected symbolically and essentially contains a differential equation that can characterize the behavior of this entire system. So, and if we were to simulate this, we would get something like this as an output. So at the bottom here we have the vertical road displacement, basically the roughness, the irregularities, the bumps in the road, which would translate into a vertical wheel movement and ultimately generate a vertical vehicle body movement. So for now, or in this graph, we just have the vertical displacement, but ultimately we will be looking at the body acceleration because I think this is the best measure that characterizes what you experience as a vehicle passenger. So to simulate the road input, we will be generating a synthetic road displacement signal. More specifically, we will do a sine sweep or a chirp signal that ranges from 0 to 50 hertz. Of course, roads do not look like sine waves. However, any road surface could be decomposed into waves, sine waves of different frequencies. So by us testing a range of frequency here from 0 to 50 hertz, we can basically generate all possible road surface excitations. And what I've also reflected here is that the magnitude of the irregularities are lower at higher frequencies than at lower frequencies. So like the big bumps, the potholes, they obviously have a much larger vertical displacement than kind of the high frequency imperfections from the road surface. So now we can formalize all this into the model. Again, shown here as a screenshot from the system modeler. And now we can provide some initial parameter values and then let that run. Put the input signal in, see how it propagates through the system, and then we get an output signal. And ultimately, we want to look at how the vehicle body responds to that sine sweep input. So for now, this input is in the time domain. So we've simulated, and that's consistent throughout our entire setup here. We've simulated 50 seconds, a time frame of 50 seconds for each experiment. And here now, instead of vertical displacement, we're showing vertical acceleration because that's what you actually feel. Now, however, as humans, we perceive waves and accelerations very different at different frequencies. So perhaps at the low end of the spectrum, we would perceive a heaving motion, the kind that can induce motion sickness. And then as we go up in the frequency range, we would feel vibrations, rumbling, rattling, all the way to acoustic noise that we can hear. So for that reason, we're translating this now. We're performing a Fourier transform, translating the time signal into we're moving from the time domain into the frequency domain. So on the x-axis, you now have the frequency range. On the y-axis, we still have vertical acceleration. Now, in this particular curve, this response curve, which is the Fourier transform of samples from the time series simulation, we see two very distinct peaks, one around 2 Hertz and another one around 22 Hertz. So 2 Hertz would perhaps be perceived as a wafting motion, whereas 22 Hertz we would perhaps perceive as a vibration or a barely audible, very deep rumble. And of course, the shape of this curve, of this response curve, is based on one particular damper setting. Also note that here I'm using a linear scale. In practice, when you look in the engineering literature, you would typically see log scales used in such a context. So now, okay. So now let's perhaps choose a excuse me a firmer damper setting. And with such a firmer damper setting, we see a significant attenuation at the peaks. But as a trade-off, other ranges have increased. Now, what that means in practice isn't so important for our exercise. However, you can imagine that engineers must make trade-off in terms of what is more important. And of course, there are many more other parameters to modify, such as spring rate, spring stiffness, tire stiffness, wheel mass, and so on. And of course, the vehicle mass isn't necessarily a parameter that you can change, but rather vehicles are used in different contexts. They have a different number of occupants. They are loaded with different payload. So there are certain parameters that you as the engineer cannot directly influence, but rather you need to be prepared that your system is subject to these different kinds of parameters. So anyway, we will now, for our initial simulation, start with textbook parameters found in one of the most well-known handbooks in literature on chassis engineering. And I'll just use those as starting points, and then we will modify them. So more specifically, what we will do is we will simulate 288 different parameter combinations, run the simulation, sample that simulation with 100 samples per second, then perform a Fourier transform, so we have frequency data, and then perform or then compute the squared magnitude of the Fourier coefficient, which we record as the power of the signal, and that is shown here in the rightmost power column. So that's the data that will now go into BayesiaLab. So that was the data that's generated from our original simulation, and then all these data points go into BayesiaLab, and with that we are trying to simplify that, or rather to approximate that, so we can more quickly try out alternative parameter values. Now you may ask, well, why not just running billions of simulation? You know, let's run this overnight and just try out all computations. You know, then can we just then look at the results rather than approximating the original simulation? Well, yes, we could do that, but then if we were to perform a billion simulations or any large number, that's kind of, to search such data is kind of a challenge in and of itself. And we're not just looking for a single optimal value, but rather what we're looking for is a distribution of frequency. We're trying to optimize that. We will have to talk about the criteria a little bit later. So it's not just running a billion simulations and then looking for the one with the single best value. Rather, we're looking for a curve that consists of many, many points. So that would be very difficult to achieve. So this is what we want to do now. We want to approximate our original model with a Bayesian network model. And there are many more conceptual advantages to that. And that is, for instance, we can represent the frequency distribution as a single variable. So that will come in very, very handy. We can visualize the relationships between individual variables. We can perform sensitivity analysis very easily. We can also simulate values that we haven't explicitly tested. So interpolation is very, very easily. And this will come in handy for simulating different payloads. We can work with uncertain inputs. So we can, for instance, optimize our parameters for a range of vehicle masses. We will, I think, use a range from 450 kilograms to 650 kilograms. Basically saying we don't know, or this car may be used in these different contexts, so we need to leave that particular value uncertain. Also, we could have multiple inputs, of course, and also multiple outputs. Now, today we'll just focus on the frequency or the power spectrum as the single output variable, but we could have multiple variables. And also very practical, Bayesian networks are inherently capable of handling nonlinearities. As you can imagine, in such a system, there are plenty of nonlinearities, and we can literally mix categorical and numerical parameters. So here this doesn't apply today, but we could use different materials, different brands of tires, and so on. I already mentioned we can optimize under uncertainty, like we don't know how the vehicle will be loaded. And then most importantly is that to this model that we machine learn, we can also introduce domain knowledge. We will use it towards the very end, where we say there are certain dependencies between, let's say, wheel mass and spring rate of the tire. So that is, we can directly introduce this into the Bayesian network. But now let's do that. For the first few slides of the demo, I will use screenshots, because this way I can put labels on the screen while I talk to the content, and then later on we will switch into a live demo. So the data set is prepared with like 1.4 million observations generated earlier. That is what we're now bringing into BayesiaLab using the data import wizard. So here I need to point out that the different role that variables play. Our very first column that we have here, that is the power column. That's the power, that's the squared magnitude of the Fourier coefficient that we got out of the Fourier transform. So that is very important, that we're not using that as a direct value, as a observation, but rather that we use that as an observation weight. And this will become relevant in the context of using the frequency, which is the rightmost column here. That's a continuous variable, and between the power, using the power as a weight and using the frequency as the observed target variable, if you will, we can, the node that we generate, we can interpret as a power spectrum. Now all the parameters shown here in pink, they have discrete states because we tried out spring rates at certain distinct levels, wheel mass at certain levels, etc. So here we just have a combination of discrete states. Now the next step in the data import process is missing values processing. Since we have no missing values here, we can skip that. Next is discretization, and as you may know, in BayesiaLab, there are many discretization algorithms available that allow you to automatically bin your data. Here, we only have one continuous variable, and that is frequency. But given the special nature of this variable and its interpretation, we're going to use here octave intervals, which is very common whenever we deal with vibrations or acoustic signals, that we split frequencies in octave bands. And here in this case, we start with 2, 4, 8, 16, 32, and higher. So that's how we split our 0 to 50 hertz signal. Now that's the last step of the data import process. And then we have our initial unconnected network. And as I was explaining earlier, the frequency variable weighted by the squared magnitude of the original signal of the squared magnitude of the Fourier coefficient, and now binned, can be interpreted as the power spectrum. That sounds perhaps quite theoretical, it makes a lot of sense when we switch into the validation mode. Now, I've actually relabeled the frequency variable or the frequency node and renamed it power spectrum. And you now see a green monitor on the right-hand side of the screen where we can observe this power spectrum. So now we have the bins arranged vertically, 2, 4, 8, 16, 32, and greater than 32. And now the horizontal bars, they represent the power in of the signal in this particular frequency range, or the power of the vibration, if you will. So actually, here is an illustration of that. So just for sake of completeness, here are the units. Now, power spectrum in this context is represented or measured in G squared over Hertz. Then suspension damping is Newton seconds over meter, and so on. So just to be complete here, let me mention this. Okay, so let's now learn our first Bayesian network, and I'll do something that's quite unusual for us. I will learn a naive Bayes network, because we have many more comprehensive and sophisticated learning algorithms available here, and usually we kind of turn up our nose at naive Bayes networks. But here, a naive Bayes network will be actually quite useful. Why? Well, here we know for sure that our input variables are independent of each other, or for now, because we have simulated those as such. We've randomly created parameter combinations of different spring rates and damping and wheel masses and so on. So those variables are indeed independent because we generated those values. And we also know that they're directly related to the target variable power spectrum, because we have created the data generating simulation, and there we have built in those relationships. So far this is simply reflecting our input. Let me now switch from PowerPoint into BayesiaLab. Just end the slideshow here. Hold on. Okay, so now we are in BayesiaLab, in a live version of this particular naive Bayes network. And there are a couple of interesting things that we can do. First of all, we could now start simulating different values. So I could say, what if I set the suspension damping to 2000? And what if I set the tire spring rate to this value? We can immediately observe how the power spectrum adjusts. So we don't have to run a new simulation. We don't have to sample thousands of data points and perform a Fourier transform. We can just directly experiment, try out different values, and perform instant inference. So that's was really our first objective for today. But let me now look at something else. Let's look at, or let's try to interpret this. And this is quite important because we always emphasize Bayesian networks are not black box models, but you can read them immediately, directly interpret them. And that's what we can do here. So for instance, what I would like to do now is I want to know which variable of which parameter that we have here influences or is most informative with regard to the target node. So I will select mutual information with the target node. This is quite relevant because, or mutual information is relevant in this context because given the shape of our target node of power spectrum, there is clearly not or we will see that there is not a linear relationship, or rather we're not interested in a single value of the power spectrum, but we are rather interested in the distribution. So here we can, using mutual information, we can see which variable provides most information with regard to the distribution of power spectrum. Here we see, for instance, suspension damping. That's perhaps not surprising, is very important. Tire spring rate is important. And then perhaps surprising, or that was surprising to me, the spring rate, your main coil spring, seems to be relatively unimportant in this context. But now this particular measure that we're showing refers to mutual information with the target node overall. Now let's say, let me move this over again, that we are trying to achieve, or we want to see which parameters are important for a particular level or for a particular band of the power spectrum. So in this case, I set below 2 Hertz as my target state, and now I can evaluate the mutual information with regard to the target state. And what is really quite interesting here, now the tire spring rate becomes much less important, whereas the suspension damping remains very important, and so on. So we could now set different nodes or different frequency bands as target states and look at this again. But there's another way, a very convenient way of looking at this, and this is using our tornado charts. I think this is a particularly useful application, or rather our tornado diagrams. And I will make this larger so you can see this on your screens. And let me perhaps go straight to the individual frequency bands. So when you look here at the top, at these tabs, 2, 4, 8, 16, 32, over 32. So we now have the tabs for the individual frequency bands, and the horizontal bars show us what share of the power spectrum the individual frequency band has and how the parameter influences this. So it basically can show us how the distribution of the power spectrum may change as a function of different parameter values. So here we can see that suspension damping can have a huge influence on the frequency band under 2 Hertz, whereas wheel mass seems to be relatively unimportant in this context. However, if we were now to look at the other end of the spectrum, over 32 Hertz, our top band under consideration, now we see wheel mass is hugely important, as opposed to, what was the other one? Wheel mass is hugely important, and others become less important. So we could now go through each of these bands and see what moves the needle for what band, basically which parameter affects the individual frequency band. I think this is really an interesting use case for the tornado diagram to get a sense of how things work in this particular domain. So let me close out of this. Now, of course, we can now try out and play with individual values, try out different parameters, but we can also systematically search for optimal values. So let's say we define as our objectives, we absolutely want to minimize the kind of the wafting motion of the vehicle. So we want to minimize the content of the power spectrum under or below 2 Hertz. So I can use one or several of BayesiaLab's built-in optimization tools. Let me go to Analysis, Target Optimization, and here I will use the genetic optimization. And what I want to do now is to minimize the probability of the state under 2 Hertz. So I will now want to search my parameters across a range, and I can set particular constraints. Here in our case, I'll just let BayesiaLab search across the entire spectrum in order to minimize the share of the super low frequency component of our power spectrum. Okay, let me run this. Okay, and this was very quick. There wasn't really much to search. BayesiaLab proposes a best solution, which is shown here in the report. I will, however, show the solution here by going into our scenario list. Basically, when BayesiaLab computes solutions throughout an optimization, these solutions get saved in or can be saved in a scenario file so that I can then subsequently retrieve them. So this would be our best solution. Here with these parameter values that are shown here in purple in the monitors, I would achieve the power spectrum here in our power spectrum monitor. I can see that now the proportion or the share of the signal of the power spectrum under 2 Hertz is below, or is right at about 0.5%, which is a lot less than what the marginal distribution would be. So that was one way to optimize, but of course, now that we've set this to a very, very low value, we have a very high share of values, let's say at between 16 and 32 Hertz. So what can we do, or how could we now perhaps perceive or try to achieve a even curve? And you know, you might think, or you may be familiar with this approach from perhaps optimizing an audio signal. You're familiar with equalizers. Many of the old stereos had this graphic or this graphical parametric equalizer where you could tune certain bands and raise them or attenuate certain frequency bands. That's essentially what we're now trying to do to achieve an even response. But of course, we can't just, you know, apply a filter to our signal, but rather what we will do, we will now need to modify our parameters in such a way that we can get close to this even signal. But now, what do I mean with an even signal, or how would we capture that here? Actually, let me just. I have a saved version of this file, but we have enough time so I can build this manually. So the way I'm approaching this is with a function node. I will go back into the modeling mode here and introduce a function node that by default has the name F1. I will connect this function node to the power spectrum, and then I will compute the entropy of that power spectrum. So I'm going to inference functions, select entropy, and pick the power spectrum here from our list of available variables. Here's only the function node is only connected to one node, so the power spectrum, so that's the only available variable here. I click on validate, and so now the function node F1 represents the entropy of the power spectrum. What does entropy mean in this context? Well, entropy is a measure of uncertainty. And we've talked about this in other webinars. We're talking about it in our book. Uh, Basically, a uniform distribution has the greatest uncertainty. If I were to, let's say, if I have a fair coin would have an entropy of 1, as opposed to a biased coin would have a value lower than that. So yes, here in this case, or rather, I'm just make sure that I'm getting the direction correct. So higher entropy means higher uncertainty, lower uncertainty means lower entropy. So if I have a completely certain observation, then my entropy goes to 0. So if I were now to, let's say, select a certain state of our power spectrum, I say this is it, that is the value, then we can see how the entropy value goes to 0. Of course, we can't do that. We can't just set our frequency response to a certain level. Rather, we need to get there by modifying our parameters. Okay, that's what we will do now. And let me perhaps show you what that could look like. Again, I'm just trying this out. We can't really do this. You know, I'm just manually creating a sort of uniform distribution. That's kind of where you want to get to, that all components of the power spectrum are about the same. Now, this would give us, for this particular node, the maximum possible entropy distribution. You'll see the precise values in the slides where I have screenshots of all that. So in order for us to achieve an even distribution of the power spectrum, we need to maximize the entropy. This is precisely what we're trying to do. So we are going to use a function optimization, and we now want to, oops, hold on, I clicked the wrong button here. We now want to set an arbitrarily high value for the entropy, and then let BayesiaLab search what is the combination of parameter values that maximizes my entropy. This would then basically get us to as flat a curve as we can possibly get. So let me run this. And this is the optimization result that now shows what the distribution would be like, the power spectrum distribution would be like with the optimal parameter values. So now we see the function value, the entropy value is now at 2.344, which is higher than what we had originally, 2.095. So that's an improvement, and we can see how the power spectrum has changed. It is certainly not yet flat at all. However, it is more even. It has reduced the peaks and increased the valleys here in this curve. So this is about as even as we can get in the power spectrum with the available parameters within the ranges provided. So in the slides, you can see this in a little bit more detail, how we went from the original power spectrum to the optimized power spectrum, and then the theoretical optimal power spectrum all the way to the right. So you may ask, well, couldn't we also, or why not do a neural network? You know, couldn't we do this more easily and perhaps more conveniently? And neural networks are on everybody's mind right now. Yes, we could model the response surface with a neural network. However, it would be an uninterpretable black box. and there would certainly be no way to introduce human domain knowledge. And there is certainly plenty of domain knowledge that we need to bear in mind as we go into more details of our problem domain. And one piece of domain knowledge, for instance, is that tire wheel mass and spring rate of the tire are related. So here we have two tires, perhaps something like, or perhaps a decision that you make when you buy a new car. You have a choice of, you never have a choice of tire diameter. The outer diameter is always fixed, but you have a choice of the size of the rim, which then affects the, or the aspect ratio of the tire, basically the sidewall height. And as you look at the left wheel tire assembly, there you have a very large rim. Perhaps that's a 20-inch rim. That leaves only a little bit of rubber at the bottom, so the sidewall is very short, as opposed to on the right-hand side, perhaps that's a, I don't know, a 17-inch rim. There we have much more sidewall. Also, the bigger rim is a lot heavier than the smaller rim. And given that the different sidewall height, inevitably the wheel on the left, the big rim on the left, or rather the tire of the big rim on the left would have to have a much higher spring rate, and at the same time would also have a higher mass. So now that's a constraint, or that's just a physical reality, and that's probably what we should consider in our optimization. Now, in our mathematical model, we can pretty much simulate anything we want. And we did. We didn't take that into account. But now that we have the simulation results, we can go into the network that we learned and manually introduce a dependence between wheel mass and spring rate, just like we looked at it. And perhaps we look at some data of wheels that are available in the marketplace, or just use some physical formula that tells us the spring rate of a tire as a function of the sidewall height or something like that, and enter that. So now we've created, and I'm just showing this as a screenshot now, we have manually introduced that relationship specified through the node editor and equation, or just provided the probability values, and with that we can optimize again, use our search function again, and get new results. And as it turns out, now our parameters are different because of the constraint we provided. So that's very important. And probably in reality, there are many more relationships between different parameters. Of course, there are many more parameters. An engineer could then provide these relationships on top of the available simulated data. So we don't have to now rerun all simulations. Rather, we can take the simulation data and add our new domain knowledge to the existing Bayesian network. So now this is basically the way an end user or researcher would work with this with BayesiaLab. But for instance, if we now wanted to share this with our colleagues, with other users, one very convenient way of doing that is via the BayesiaLab web simulator. So we can now take this model as it is and define icons, logos, we can specify the number format and so on, and then publish this network via the BayesiaLab web simulator. And this is what it would look like in our, as I email you the slides from today and the video recording, I will also share a link to the live web simulator, so you can experiment with different wheel masses and vehicle masses, spring rates, damping rates, and so on, and then see how that affects the power spectrum and how it affects the entropy. So you can now interactively work with that, and anybody with web access can experiment with that. Now, this web simulator is just one of many web simulators that we have on our BayesiaLab web simulator server. Many of our clients post public web simulators, simply interesting problem domains. Of course, you can also share your engineering problems or whatever you're working on privately. For that purpose, we have private web simulator accounts. So you can build a model locally on your desktop, send it up to the BayesiaLab web simulator server, and please note here, you're only sharing the model, not the data, so your data always remains local. And then once it's on the web simulator server, then you can determine, is it something you want to make publicly available or just privately to a select user group. So that brings me to the conclusion of our webinar. I see we have a number of questions via chat, but we're starting to run out of time. So all the questions posted via chat, we will answer offline and thus address these questions. Let me just talk about some of our course program. So if some of you are now interested in learning more about Bayesian networks and BayesiaLab, we have quite a number of courses scheduled around the world throughout the entire year. The next course is coming up next week in Dubai, in the Emirates. Then in March, we have a course in Washington, D.C., then in Amsterdam, Singapore, Sydney, Paris, Seattle, and so on. This is really a great way to really learn in depth about BayesiaLab and make it useful for your work. But beyond that, we have many other events, webinars, seminars. We are about to announce a new series of events for the Asia Pacific region. So please stay tuned and check our calendar, our event calendar on our website. We'll probably have an event somewhere near you. Now, everything that you've seen today, you can try out yourself. As I said, I'll make the data, the networks, everything available, so you can very quickly and easily build your own simulator. There are two versions available of our trial. One is more of a demo version that's quite limited in terms of the nodes, in terms of the number of nodes. So I would recommend you to download, or rather to apply for a 30-day evaluation version that is unrestricted. So that has absolutely the same features that you've seen today in my demo. And then we have an active user community. You may want to register. For instance, you can discuss today's webinar and what you found interesting. We will also post answers to any questions on this community forum. A great way to explore the world of Bayesian networks. Then there's also a great opportunity to meet many other BayesiaLab users, and that's as part of our annual conference. Last year we were in Chicago. This year we will be at the North Carolina Biotechnology Center in Durham, North Carolina. Very nice facility. We expect participants, BayesiaLab users, researchers, scientists from all over the world to present at that conference. It's a great way to connect with other users, to learn tips and tricks from them, and it's also a lot of fun. So I encourage you to consider joining us this October in Durham. So with that, I think I've just about used up the entire hour. I'd like to thank you for your time and interest. As promised, I will answer the questions offline and post the answers in our forum, but also feel free to connect with us on LinkedIn, on Facebook, via Twitter, or just feel free to email me directly or any of my colleagues. Here are our contact details, and I would really love to continue the conversation. With that, thanks again, and have a great day.